Hello, this is the first episode in a series of a couple episodes about background processing in functional Scala. So in this one, I'm going to focus on three things. What does it mean for something to be a background process? Then I'll show the traditional Scala approach to tackling this problem. And then I'll show the basic approaches to handling background processes in Cat's effect. The whole series will not be focused on a particular library, but in this episode that's all I can do if I want to fit in the time span. What does it mean for something to be a background process? We can think of processes in our applications in two categories. One of them would be the foreground process, and the other one would be the background processes. Let's say you have an HTTP server, someone calls your application with a request, and then you have to provide a response. So whatever you are doing to provide that response is the foreground. That's the work that someone actually asked for and wants you to perform because they actually need the response back from you. But that might not be the only thing your application is doing. Maybe it's running some scheduled jobs in the background to maybe refresh some bank account balances, or maybe to refresh the score of the user, or maybe to distribute messages from all the users in the application so that they are routed directly to the users they are meant for. Basically, whatever runs that is not directly part of what needs to be done to provide a response to the user who requested the action, that is the background. So it's not what the user sees directly, but something that happens sort of behind the scenes without user interaction. But it can still be triggered by user interaction. For example, a user submits a background job. So they make a request to start processing a CSV file, but you don't start processing it immediately. You just schedule it for later, or maybe put it on a queue, and then in another process, a background one, you would take elements from that queue and change them into processing jobs. So just to sum it up, whatever is outside of the main flow of execution, that would be a background process. Now, the traditional Scala approach to handling background processes is usually just starting a feature and not waiting for it. That's the simplest thing you can do, because otherwise you can create like a scheduler and submit jobs to it, but that's on a slightly lower level. And the highest level you can probably go to, aside from starting a stream, which is beyond the scope of this video, is creating a feature and letting it run, just not waiting for the result. So let's look at what that looks like. So I created here a feature that blocks the current thread for 1 second. Whatever this feature does, it doesn't really matter. I just wanted to show an example that actually takes some time to complete. And I have two helper functions that will do essentially the same thing, they will just create a feature using the function I described earlier. And now there's a couple ways in which we can combine the results of these two functions. So one of them is running these features sequentially. So in this example, I have a for comprehension in which I first run the p1 function, creating a feature. I flat map on it because that's what the arrow with the sugars do. And then when that is done, I run the next feature, the second one, and also wait for it. And then when the whole thing is done, I yield a unit. So the whole thing will take approximately 2 seconds to complete, but definitely not less, because each of these two parts needs to run in a sequence, so one after another. We can also run two features in a different pattern. We can create both features before the for comprehension and then flat map on these features, but they will now run in parallel. What this means is that at this point, when we create a feature, we have nothing else running at the time, so it's okay. But when we are creating the second one, the first one is already running. So if we are now creating the second one, we have two features doing the same work running together in parallel. And now we can flat map on both of them so that we will wait for both of them to complete, but they will still keep running independently. And it is only the process that actually triggers the whole for comprehension and the creation of these features that has to wait for something. But the features, they are not waiting for each other. They just complete whenever they actually complete, and they run at the same time. So these two approaches are relatively reasonable. They are quite safe. We just run one thing after another, and otherwise we can run two things in parallel and we wait for both. So we know that if there are any race conditions, they can only happen in the parallel part. Only in the case that these two futures are operating on the same state, a situation may happen that they will corrupt each other's data. But there's no other like risky behavior that can happen. Like if the whole process finished, but there would still be some outstanding work to do, and some other background process would still be running. And that situation can be easily replicated with this. So we start two futures in the same way as before, but we only wait for one of them. Doesn't matter which one, it's just the same implementation underneath anyway. But we only wait for one, and then we immediately yield. So the future returned by this function will be completed when only one of these futures is completed. But let's imagine this one takes an hour to complete, and this one takes like a second. So after a second, we would have exited from this run parallel forget one function from the future returned by it, but this hour-long job would still be running. So that's probably not the situation that we want to be in for several reasons. So one problem is wasting resources, because sometimes we start the job in the background, but then maybe our main program fails and we decide that we no longer need the value from the background process. So maybe we want to stop that, just interrupt whatever that is happening there and allow the program, the background program, to free up the resources that it's taken. So if we don't do that, we might actually cause the resource pool to be exhausted, and then no one else will be able to use these resources. So if we had a database connection pool and we started a bunch of background jobs, each using a connection, and the pool was bounded, then eventually we will run out of connections to use. So no more jobs can be started then until the old ones are complete. But of course, if your goal is to run things in the background and keep them running whatever happens, then of course that might be the solution you're looking for. It's just worth keeping in mind. And in fact, if you have a background process that is supposed to run forever, for example, a message processor, something that takes messages from a queue or a stream and does something with them forever, like as long as there are incoming messages, then if you have something like that, then it's perfectly fine to keep it the background process, kind of forgetting it. But it still leads to some problems that are more visible when you want to actually stop the application, or maybe you are running that in a test. There are certain situations where when you actually want to stop a background process and do it gracefully. So if you're just starting it as like a future, or if you just start it and get a unit back, then there's no way you can use that to stop the process. So you need to kill the JVM or do some other terrible stuff, or manually flip a flag somewhere, call a method like stop on a global message processor object. These are some quite shady approaches to solving the same problem. So as I mentioned, maybe you have a test in which you start a message processor and you want to send it some messages, then close it, verify the result of the processing of the message processor, and then run another test. So if you just start a process in the background and you get nothing back, no handle that would allow you to stop it, it becomes extremely hard to do this without having a bunch of consumers or message processors running in the background when you no longer need them. And it can also cause data corruption. One example is what I mentioned before with race conditions, but another example would be when you have one process and some condition changes and you want to stop that process and start a new one with new information. So if you fail to replace the running process, if it still keeps running and you start another one, then they will maybe concurrently take messages from each other. So there are several reasons not to forget background processes. Does this mean that there's no way we can start a process in the background and still not wait for it, but have control over it? And there are ways to do that. So I'm going to explain one way to do this, a very low level way to do this in Cat's effect today, but we will get back to this problem and the solutions in later videos. So here's a program quite similar to what we had before with futures, but this time we are not using futures at all. we will be using cat effect IO. So in case you're not familiar with it, an IO is a description of a program that can be run with other programs and eventually executed to provide like a future, or synchronously executed to provide a value at the point you're asking it to. But for our purposes, it's just a building block that you can combine with other instances of the same type of IO of something, and you can do this in several ways. So here I define such a building block as a sleep. It's very similar to what we had with future before. So this, when I actually execute this, because this is a description, when I make this description a running program, it will complete in 1 second. So I can have 2 such programs, and now I can run them sequentially, so one after another. When the first one completes, start the second one, and then yield. Notice that the difference between this and future is that these are vals. So I'm actually assigning these units of work, these building blocks, to values before I start the for comprehension. But this doesn't mean that they are already running. These are still just descriptions. They only become programs when I sequence them using a for comprehension, or when I pass them to the runtime, or when I just hit the unsave button. So that's the sequential variant. Now we can also run 2 IOs in parallel using the per product combinator. It's just one of the methods that we have on IO that can combine 2 IO programs into one. So far, so good. We are doing the same things that we did with future. We run the IO in a sequential manner, and then we run 2 of them in a parallel manner. And there's also other ways to do this, not using the per product operator. That's just the one that I chose for the purpose of this. But there are other ways to orchestrate how 2 IOs are being run. So I'm going to reproduce the case that we had from future, where we started 2 futures concurrently and only waited for one, but let the other one running in the background. So here we have the same thing. I'm starting one IO to run in the background, and then I'm waiting for the other one. And this does not actually like return unit or anything like that. It actually gives me a handle, something that I can use to orchestrate this process. So it gives me a fiber. I'm going to explain what the fiber is in just a second. But at this point, when we are in this part of the for comprehension, this IO, this P1, is already running, but it doesn't need to have completed by this time. So this is quite different from what we had before in the sequential version, because at this time, when we create P2, when we map on it, then P1 has already completed and it has already succeeded. But at this point, we know nothing about whether P1 completed or not, because we started it as a fiber. Let me explain what a fiber is. A fiber, in Cat's effect, is a description of an already running computation. So it's almost like a future. So it's something that you get from running an IO using start, but it gives us much more power. First of all, we can join on it, so we can convert back to an IO. So even if you start a process in the background using start, you can still await on the value if you want to. And you can do this anywhere else in the application. So you can pass a fiber to a function and maybe await on the result somewhere else. Or maybe you want to pass a fiber to like a global pool of fibers that are running at the same time. Very importantly, we can cancel the fiber. So we can ask the runtime to just stop the IO that has been started and gave us a fiber. So a cancel token in here is just an f of unit. So if I said fiber.cancel, that is an IO of unit. So if I run this code, I would start the fiber using the start method, and then I would cancel it immediately, and then I would wait for P2. So maybe the first IO completed, maybe not. In this case, it would probably not even start because we are canceling so fast. But maybe if I cancel it after I finish P2, then now it gets more interesting, because now we are not leaking any kind of work into the background after our run parallel for get one operation is done. So we are starting the first job, starting the second job, and then we just cancel the first one if it's still running. If it's not running anymore, it will just not do anything. This cancel will just complete, and that will be it, because there's nothing else to cancel anyway. we can work with fibers in a variety of different ways. We could maybe say that if the second IO fails, then we want to cancel the first one. And that would still make sense, because if someone runs the whole thing, like run parallel, forget one, if this fails, it is probably because P2 failed. Nothing else can fail in here. Start will not fail, and only P2 can fail somewhere inside of it. We know that it will not because it's just asleep, but maybe it's something else that can fail. So in that case, if it failed, maybe you don't want to keep the other one running. Maybe you just want to cancel it in that case and not waste any resources. So this is just a couple of ways we can use fibers in, and that's actually it for today's episode. I hope I sparked some interest in you about orchestrating background processes in functional Scala. We will dive into much more detail in other videos, but for now that's pretty much it. So the main takeaway of this video should be that I/O provides us a more robust way of working with background processes, because now we can start something and cancel it afterwards, or decide to cancel it depending on some other conditions. And it's built into the data type, into I/O. We can build I/Os that react to being cancelled in a variety of ways. This is actually what I talked about in one of my talks last year. So this is it for today. So if you like this, please subscribe to the channel so you don't miss the next parts. Please slap like, and I will see you in the next episode.